Guys, welcome once more to our YouTube channel. For those of you who are taking physics on Thursday GCE 2023 session, wish you all the best. Be you go rocket. So let's have a quick look at Northwest Mock 2021 as part of your revision process. Okay, let's go. Okay, guys, so this is our question 6 all. So go ahead and just pause the video and check it out and see if you can solve it. All right, if you cannot, then check out what I've done. So this is the first part, an inductor and a resistor. So just go ahead and read. So um, we can read, and then let me just show you what you can read, and let's just solve. So this is how the current would vary in that circuit, in an inductive circuit. Okay, so an inductor is really trying to slow down how quickly the current reaches its maximum value. Okay, so exponentially increases to its maximum value. That's really what is happening. That's the variation there. So the examiner asks you to explain briefly how the current would vary in that circuit. So when the switch is closed, the current exponentially grows from 0 to a steady value of current when the back EMF across the coil drops to 0. I'm going to explain to you why this thing is happening like this. So first off, let's calculate the steady current. Okay, the examiner says determine the final steady current in the circuit, which is this I0 like that, which is the peak current in the circuit. Okay, so to get that steady current, of course, is E over R. So the EMF is 12 volts divided by the resistance of the resistor. So we get 3.0 amperes. That's our maximum steady current, or that's our steady current. So statement 3 says determine the rate of change of current in the circuit at the instant when the current is 2 amperes. So when the current is 2 amperes, remember that it's not yet reached its maximum value now. So it's somewhere around here. So here, the current is speedily changing with time. All right. So let's calculate the rate at which this guy is changing with time at this instant like that. So again, we're going to use Kirchhoff's voltage law. The EMF will be equal to the voltage that is dropped across the inductor plus the voltage across the resistor. Okay, sorry I've not really drawn it. I should have drawn the circuit, the inductor, the resistor, and then the EMF. So you can see all of them in series like that. But again, you can go ahead and draw it. Okay, so you notice that the EMF will just be dropped across the inductor and then the resistor. So once the voltage drop across the inductor, hey, it's L didt. All right, that's how much back EMF. The voltage is really a consequence of the back EMF across the inductor. Okay, and that's how I get back EMF L didt. So make didt the subject. So you're going to get didt as E minus IR, right? So send IR that way over L. So our didt is going to be 12 minus IR. So at that instant I is 2 amperes, R is 4, divided by the inductance of the coil, which is 1.8 henries. So our didt is 2.2 amperes per second. So that's how fast this current is changing. Okay, so it's increasing by 2.2 amperes every second at that particular instant. Okay, so that is it, guys. That is it for the first part of the problem of our EDAP question. So the next part says, yeah, you can read it, right? So let's solve it. So we have that elastic potential energy, because we are stretching the material, right? For every stretched material, the elastic potential energy is half kx squared. So but k is lambda over L0. Okay, this is a connection between engineering and physics in advanced level. You don't really get to talk about the relationship between K and modulus of elasticity of a material. This is lambda, here is modulus of elasticity. Okay, it's not wavelength, guys. All right, so our lambda is also EA. Okay, so you notice that in physics you talk a little bit about Young's modulus and the spring constant, but you don't find a connection between them. Okay, you don't talk about a connection between them. In mass mechanics, you talk about modulus of elasticity, but you don't find its connection to Young's modulus. So yeah, we can find those connections. So K is EA over L0. So you notice that lambda here, which is modulus of elasticity, is basically the Young's modulus multiplied by the cross-sectional area of the material. Okay, good. So that's our K there. So you notice that our elastic potential energy, which is normally half kx squared, this is what we use in physics, this is what physicists know. So K now is EA over L0. So put K there, you're going to have EA x squared over 2L0. So assumption, what is the assumption? The elastic potential energy stored in the stretch catapult is converted to the kinetic energy of the stone. Very important. That's why the examiner says state any assumptions made in your calculation. So we have stated it already. So our elastic potential energy is this. All of that has to be equal to the kinetic energy of the stone. So you notice that we'll make U the subject. You have this guy first. So U squared is that. So our U is about 22 meters per second. Thank you guys for checking out the content. Hope you enjoyed it. If you got anything and you really like, maybe something that you understood, please leave it down in the comment section below. Wish you all the best in your exams. See you soon.